Hey guys, today we're going over 3D Cartesian force vectors. We'll go through the 3D space, unit vectors, coordinate direction angles, and then we'll solve two practice problems. A 3D Cartesian space can be mapped using a right-handed coordinate system defined by the axes x, y, and z, or z if you're American. With your right hand, you defined the positive orientation of each of the three axes. Your thumb defines the positive z-axis. Your fingers run along the positive x-axis, and when you curl your fingers, they define the positive y direction. If you don't have a thumb, you can do the same thing using your dew claw right side up. These three axes divide space into 8 octants. Any vector can be broken down into components made up of pieces that go in each of the 3 primary directions. This fact helps us combine multiple 3D vectors by summing their matching components. Let's look at an example of a vector in the 3D Cartesian space. Here we have vector f. Its tail is at 0, 0, 0, and its head is at 5, 3, 4. The rectangle is just to help us visualize the vector in 3D space. F can be broken into 3 components along each axis. I, j, and k are unit vectors in the direction of x, y, and z. A unit vector has a magnitude of 1. So what this is really saying is that our vector has components made up of a scalar 5 multiplied by a unit vector in the x direction, a scalar 3 multiplied by a unit vector in the y direction, and a scalar 4 multiplied by a unit vector in the z direction. That means that the magnitude of our vector can be written as the square root of the sum of the squares of each of the components. Our vector f has a magnitude equal to the square root of 50. A vector is made up of a magnitude and a direction. To describe a vector's direction, we use things called the coordinate direction angles. Alpha, beta, and gamma are angles measured between the tail of your vector and the positive x, y, and z axes. They are always between 0 and 180 degrees. The cosines of each of the angles are equal to the force component in that direction divided by the total force magnitude. To find the angle values, we would take the arc of the cosine. For example, that would give us 45, 65, and 56 degrees for alpha, beta, and gamma. If we had a unit vector in the same direction as f, then we can describe it using only our direction cosines. Since the magnitude of our vector is 1, that means this is a very useful thing to know. That's because unit vectors are used to define the direction of a vector. So for f, we could write our cosine values describe what proportion of the total vector magnitude is going in each of the 3 primary directions. That's the gist of the concepts for today. Problem 1. A force F is acting on a brachiosaurus. The force has a component acting along the y-axis of negative 50 pounds and a component acting along the z-axis of 90 pounds. The force also has an alpha coordinate direction angle of 65 degrees. What is the magnitude of the force? We want to find the magnitude of our force in 3D space. We're given 2 of our force components and 1 of our coordinate direction angles. We can find our magnitude by combining all 3 of our force components, but we're only given 2 of them. So we're going to have to use our coordinate direction angle as related to our x-axis in order to determine our fx component in terms of our total force magnitude F. Then we can take our formula for the magnitude of our Cartesian vector, and we substitute in our value for fx in terms of f. From here, we should be able to solve for our f value. And sub in the numbers that we were given at the beginning of our question to find that our magnitude is equal to 113.6 pounds. Forces F1 and F2 are acting on Mr. Ducky. The resultant force on Mr. Ducky has a magnitude of 120 kilonewtons, and the coordinate direction angles of beta at 105 degrees and gamma at 60 degrees, as shown. What are the magnitude and coordinate direction angles of the force F2? Solve to the nearest whole number. The forces F1 and F2 are summed together to give us our resultant vector. We know two of our coordinate direction angles for the resultant vector, as well as its magnitude. We're also given one of our forces and its direction. What we want to know is what the other force has for a magnitude and coordinate direction angles. To do this, we will find the y and z components of F2. Then we'll find the missing coordinate direction angle of our resultant. Third, we'll find the x component of our resultant. Then we can find the last component of F2. At that point, we'll be able to solve for our answers: the F2 magnitude and coordinate direction angles. Try hitting pause and following these steps first to see if you can get the same answer. Fr is equal to F1 plus F2. And we know that our Fr has force components in the y and z directions because of the angles we were given. But F1 only has a force component in the x direction. That means that whatever makes up the y and z components of Fr must be equal to our y and z components of F2. So we can solve for our F2 components directly by finding out what those components are for our resultant. Now we want to find our resultant angle alpha. To do that, we're going to rearrange this formula. Which, depending on if we have a positive or negative square root, will give us an answer of 34.3 degrees or 145.7 degrees. Because we're taking a square root, we don't know if this term is supposed to be positive or negative. This answer comes from assuming it's positive, and this answer comes from assuming it's negative. Coordinate direction angles can be between 0 and 180 degrees. So we need to look at our graphic to see which answer makes sense for our scenario. Alpha goes from the tail of our force to the x-axis in the positive direction. Our resultant has a positive x orientation, so our angle alpha will end up less than 90 degrees. That means that our answer is that alpha is equal to 34.3 degrees. With alpha, we're able to solve for the x component of F2 because the x component of our resultant would be equal to the summation of the x components of F1 and F2. We get that F2x is equal to 49 kilonewtons. At this point, we have all three of our components of F2, which means we have everything we need to solve for all of its coordinate direction angles and its magnitude. The magnitude of F2 is equal to the square root of the sum of the squares of each of the components of that force vector. So the magnitude of F2 is equal to 83 kilonewtons. Now to find our coordinate direction angles, we take the arc cosine of the component divided by the magnitude. And done! Great work today, guys. See you next time.